And so basically, what we have seen in recent years is that there have been a lot of advances on the quantum supremacy or quantum advantage using different physical systems. So, for example, there was a recent um, experiment being done using photons in the group of UCST in China, where they showed quantum computational advantage over classical systems. And then there also have been an experiment in Google using superconducting systems, um, and not just on the quantum advantage on the computing side, but there also have been a lot of experimental progress in the quantum communication systems. For example, there have been a secure communication between two different cities, in Austria and in China, over 7,600 kilometers. And also there have been an entanglement-based secure quantum cryptography protocols being implemented over like 1,000 kilometers. So we have been seeing a lot of progress in last 5 years in the physical systems. And so building all this means is that building quantum computers is very hard, but not impossible. And so hardware is working. So we need to work on what is next. And so from theory side, basically the main question is we need to find applications for quantum computing. So in this talk, I'll be mostly talking about a subfield of this, which is on quantum internet. And this is where my research focuses on. So basically, let's see a scenario of the future of internet. And so in this, we mostly think that quantum internet will radically improve, or like will improve the same technology, same as the classical internet, and will moreover will be able to accomplish tasks that we cannot accomplish over conventional internet. And so one example that you might have heard before is of quantum key distribution that we cannot achieve classically. So it is difficult to predict as now what are the new applications of quantum internet, but like we have seen for classical internet, we can only wait and see what the future is. And so most of the communications will be quantum, if not all. And so there would be a scenario where, of course, we cannot replace classical internet, but we'll definitely see a hybrid systems of quantum and classical internet. And so by quantum internet here, I mean connections over quantum channels. And so a more realistic setting is definitely where both quantum and classical channel coexist. And so the setting that I'll be talking mostly about is this hybrid quantum classical networks. And so basically, just to see what kind of functionalities we could achieve in this hybrid quantum classical networks is basically these are the stages of network on the left-hand side. And on the right-hand side, we know some of the known applications with these different stages of quantum network. And at the bottom is the most primitive stages of quantum network, and the topmost is the full quantum computers. And so we can see that quantum key distribution basically only needs trusted repeaters and no other computing devices. Similarly, if we go higher on this hierarchy, we see that if we want to implement some secure cloud quantum computing or some device-independent protocols, then we would need more or less some quantum memories on entanglement generation settings. And so far, we have been able to realize entanglement generations over few thousand kilometers. We have been successfully able to prepare and measure qubits with very high fidelity, whereas we are still at a bit nascent stage for fault-tolerant qubits. And so the kind of functionalities that we could achieve is something on this level at this point. So we could see experimental implementations of QKD and also some simple protocols for key agreements and simple leader elections and delegated quantum computing stuff. So basically, I'll be talking on, in this talk, I'll be talking on two main applications in this setting. And more specifically, I'll be talking on mainly on this blind quantum computing, which I'll explain in detail what does this means. So basically, the setup is we have a user and we have a server, which is a cloud. And the user wants to delegate the computation to server, like we do even now with our conventional computers that we use, phones and simple devices, to delegate our computation to the remote servers. And then we want to compute our functions using this cloud. And so this is one kind of setting that I'll be considering in detail. And the other setting that I'll be interested in is when we have two different users. So we have user one, we have user two, and then they want to collaborate and perform some joint computation using either some cloud services or they just want to collaborate among themselves. And this is a very common functionality that maybe this user two is a hospital in charge and this user is a patient. And they want to collaborate to compute some functions that is confidential to the patient as well as to the hospital. At the same time, they want to maybe use these services as a as over a cloud or in just some joint collaboration. And so this is also a setting which is very relevant in our usual practical life. And so both the settings require security concerns. And so in this talk, we'll be considering these two settings as well as some other simple cryptographic tasks that would be useful for other applications. And so basically, we know that delegating calculations to remote systems have a very strong practical and economic motivation, especially to users who don't have access to those resources at their own labs. And this is true in our current scenario where the quantum computers won't be likely available to all the users. And so we have remote systems, for example, at IBM, Google, and all those big corporations or big national laboratories. And people who don't have quantum resources would like to delegate their computation to these systems, maybe at the cost of some money or some other incentives. And so this will bring myriads of security concerns. And so how to deal with the security concerns, what are the implications of the security concerns and consequences and ethics? These are the questions that are definitely of interest. So this talk will be mainly concerned with these two settings and their security concerns. And I'll also go into a bit detail of the implications of these settings, not just from practical point of view, but also from philosophical point of view for testing quantum physics, as well as its implications in complexity theory and different branches of computer science. So I'll try to cover some of the basics, but if there's any question, feel free to interrupt, or I'll also stop in between if there are any other questions. Okay, so maybe let's start with the part one, which is the setting one, which is delegated quantum computation. And so in this setting, we have a client. So I'll keep on calling this client as Alice. And we have a server who I'll just denote with Bob as an entity. And so the setting is the client has a very limited computational resources. I'll more formally define what does limited computational resources mean. But the user or the client, Alice, wants to use quantum computer, but she doesn't have quantum computer. Maybe she only has device to prepare photons, or she has just the classical computer, like the usual computer, or just the phone. At the same time, the server, who is maybe either these big corporations or some national laboratories, has a full quantum computer. So we are talking about noiseless, large-scale quantum computer. So I'm going in a bit of ideal setting, although we are not in this setting at this point, but for the purpose of this talk, whenever we say Bob has quantum computer, I'll always assume it's a noiseless, large-scale, fault-tolerant quantum computer. And assuming the server has a quantum computer and is able to help and provide cloud-based services how to perform this delegated computation over cloud for when the functions are quantum functions and not just classical functions. So before going into this, like I said, client has a weak computational resources. And so what does this mean? To define this more formally, one way to deal with is like looking at complexity theory. And so there are different, from computational complexity theory point of view, there are different classes of problems. So for example, the well-known problems are P and NP. So P is the class of problems which are quickly solvable by a classical computer. Similarly, NP is the problems that can be quickly checked by classical computers. So these are the two complexity classes that you probably have heard a lot, and there's a big open problem whether P is equals to NP. That means whether the problems that you can solve on a classical computer, are these also the problems that you can efficiently check their solutions. And so then you can keep on generalizing these kinds of problems, and the generalization is known as polynomial hierarchy. So in theoretical computer science, people tend to make a hierarchy based on the hardness of the problem. And so similarly, the quantum analog of P or BPP is known as BQP. And so BQP is the class of problems where quantum computers can efficiently solve them. So it's a large class of problems, and it definitely contains P because because we know that classical computers are a special case of quantum computers. However, we believe that BQP is not in NP, and we don't have a strong evidence, but we do have oracle separations between them. Yeah. Are there any questions? Okay. So then what is the quantum analog of NP? And so a quantum analog of NP is also called as QMA. So QMA is a class of problems that can be efficiently or quickly checked by a quantum verifier, so a quantum computer. So basically in QMA, it stands for quantum Merlin-Arthur. So it's a generalization of MA, but for just for rough purposes, I'll just call it a quantum NP. And so basically the much, yeah, so just to give a more detailed hierarchy of these complex classes, we believe that QMA contains NP, and also BQP is in QMA. And even another class of hard problems is known as P space. And so P space is all the problems that you can compute with polynomial space. And so basically when I say a client has weak computational resources, I just meant that client doesn't have the power to solve all the problems in BQP. Whereas Bob has a full quantum computer, so I would assume that Bob can solve the problems in BQP. So he can solve all the problems that lie here, whereas client can maybe only solve problems that lie here and not the full BQP. Yeah, so another interesting class of problems that I'll deal with is something called interactive proof system. And so in interactive proof system, you have two entities. There is a prover and there is a verifier. And so it's same as NP and quantum NP, but basically in interactive proof system, you allow multiple rounds of interaction between a prover and a verifier. And so the goal is prover and verifier get some problem statement X. And after interacting with so prover is unbounded. and verifier is bounded. And by bounded, I mean the computational power of verifier is somewhat weaker, maybe somewhat here, and the prover is on this hierarchy somewhere here. So this is like the hardness of the problem. And so a weak entity verifier would like to know whether this X belongs to some language or not. And so it would interact with the prover, and in the end, it would output accept or reject. And so this is modeled using this interactive proof systems. And people have shown that if you assume an unbounded prover and a bounded verifier, then the class of problems that the verifier can verify is actually equals to P space. So basically, just this interaction gives a lot of power to the verifier to verify these problems efficiently. So only in one round, you could only do NP or MA, depending on if the verifier has randomness. Similarly, if the verifier is quantum, then in one round, we call it QMA. Whereas people have shown that if you include interactions, then P space is equals to IP equals to QIP, which is the quantum interactive proof system. So these are like some of the broad overview of like results and complexity theory. And the reason I explain is I'll keep on using these terms, interactive proof systems or BQP, later in the talk. So yeah. So let's go back to our setting where we had a weak computational client. So basically what I meant is client is not equals to BQP. It's somewhat weaker in that hierarchy. Whereas server has full quantum computer, that means he can solve all the problems in this class BQP. And so now client wants to compute a problem in BQP, but she doesn't have resources. And she wants to delegate this to a server who can solve it. So one way to do it is client can just tell the problem that please solve this problem X for me. However, the problem with this is that server cannot be trusted, or client just wants to hide the data. So she doesn't want to reveal the data. Maybe this is an algorithm that client came up with, which could cure cancer, or which is like a vaccine for COVID, let's say. And she doesn't want to leak it to everyone. So this could be confidential data or some commercially sensitive data. And so for this purposes, client just cannot directly tell the problem statement to the server. So what we need is some way to define security. How can a client delegate this problem or outsource this problem to server without leaking the data? And at the same time, would also want to make sure that the server is playing honestly or is behaving honestly. Because if server starts deviating, then client needs to know that server is deviating, maybe because client paid some amount of money to solve the problem. And so for this purposes, there are two flavors of security definitions that we are concerned with. So one is called blindness. And in blindness, basically, what we mean is that privacy of client's computation is preserved. So if client has some computation, f of x equals to y, and she has x is her data, and f is the function that they want to compute. So she wants to hide the data. At the same time, she wants to be able to compute this y. So this is, if she can hide the data, then we say that the protocol has achieved blindness. And the second property that we are interested in is verification. And so basically this means that the integrity or the correctness of the desired computation is ensured. And so what does this mean is that if the server starts deviating from the algorithm or from the protocol, then client should be able to detect the cheating. So this is different from blindness. So basically in blindness, we only concerned with privacy. Maybe server could deviate and client would not be able to detect. Whereas in verification, maybe server knows the problem statement, but we want to verify that the problem statement has produced the correct outcome. So these are the two properties that we would like from our cloud computing protocols to satisfy. And these are the two main ones, but at the same time, we also want our protocol to satisfy some other requirements. And so this is, again, same, the client is here, and this is Bob, who is a quantum computer, and client has some function that she is interested in. And maybe they have an interactive protocol that they interact multiple times. And so the kind of requirements that we mainly are interested in is, first is the round complexity. That means we want to minimize the number of rounds of interaction between. So this is round 1, and this is round n. And so ideally, a protocol would be good if there is less rounds of interaction, maybe just 1 round of interaction. And especially for quantum interacting with quantum computer, this is even more important, because we know that coherence is a big problem in quantum computing systems. And so these have a very limited time of coherence. So we don't want to interact with it for 10 minutes. And then, because the quantum computer will just decohere in that time. So that is very important to reduce the round complexity. Second is minimum resources. So we want to use minimum resources on Alice's side, maybe only a phone or a laptop, and no quantum devices. So it would be really nice not to have any quantum channel between Alice and Bob. Third is design. So we want our protocols to be modular and not complex, because then it's much easier to optimize. And similarly, the other security concerns are security-wise. So we want a very high standard of security. So there are multiple levels of security one can consider. So information theoretic security means that we have privacy against an unbounded Bob. So by unbounded Bob, I mean that Bob is all-powerful system, not just BQP, but he can do anything he wants as long as he follows physics, laws of physics, quantum physics. But if we have blindness even against an unbounded Bob, then we say that the protocol is information theoretically secure. Whereas computational security means this privacy is only against bounded Bob. And by this, we mean that maybe a Bob who has a quantum computer cannot break it, but maybe an unbounded Bob can break it. So this is strictly weaker than information theoretic security. So ideally, we would like our protocol to be information theoretically secure, but we'll see later that some of the times it's just not possible to achieve information theoretic security, and we'll have to deal with computational security. And computational security usually comes from some hardness of mathematical problems. For example, factoring. Factoring is only secure against computational parties. So, and at the same time, there is another notions of security, which is standalone versus composable. So standalone means that the protocol is secure in single run of the instance, whereas composable security means that this protocol, a protocol P, is composable if P can be run in any environment. And so basically by a new environment, I mean as a sub-protocol of a bigger execution, or maybe it can be run multiple times in parallel and in series. And so if a protocol is secure in this composable manner, then this is much stronger security than just the guarantee that the protocol is secure in a one run of instance. And so ideally, we would like our protocol to be information theoretically secure, as well as it should be composable with other protocols. That means it should behave nicely with other runs of the protocol. because on cloud, we might have a lot of instances of different protocols, and we will not have control over what other protocols are running with our protocol. So other requirement that we would like is the class of computations to be solvable. So we would like to have as big class of computation to be able to be solved by a quantum server, and not just some restricted class of computations. And finally, we would like to have verification. That means we would like a procedure where Alice could, in the end of the protocol, Alice could have guarantees that the protocol was run correctly by the Bob. So all these requirements turns out to be quite an essential features of any delegated quantum computing protocol. And so let's see classically what we know about this. So if we forget about quantum computer for now, and if we assume this is a classical computer, so let's take a very weak client. Then classically, we know that computing NP hard function. So if this F is in NP hard, so basically NP hard is the class of problems that are at least as hard as the hardest problems in NP. So computing NP hard functions securely over a cloud classical computer is not possible in information theoretic security. And so when I say not possible, I just mean that it has unlikely consequences in complexity theory. So polynomial hierarchy, that is the generalization of NP, that collapses to the third level, and which people believe not to be, which people don't believe that would be true. So this is unlikely. So that means that even a classical user cannot delegate NP hard functions in an information theoretic manner. And so this was a result from 1987. And on the other hand, we know that if we sacrifice information theoretic security, and if we are happy with computational security, then there have been a lot of progress in this problem of delegating or computations or encrypting. So basically, this is also known as computing on encrypted data. So in this setting, there is a lot of progress in last decade or so, and this goes under the area of fully homomorphic encryption schemes. And basically, the security achieved there, we have only guarantees against a computationally bounded server. So basically, we know that, for example, if these FHE schemes are constructed from lattices, then we know that we believe that lattices cannot be solved using a classical computer or a quantum computer. So as long as the server is bounded to BQP, we know that a fully homomorphic encryption scheme is secure. So I won't go into details of those schemes, but in this talk, we are interested in what happens to quantum functions. Can we have quantum fully homomorphic encryptions? Or more broadly, can we have information theoretic delegations of quantum functions with a quantum computer? So I'll just briefly cover what has happened in this field over the past 2 decades. So this problem was first considered by Andrew Childs in 2001. So by this problem, I mean the cloud quantum computing problem. And so there, the child scheme consists of a powerful quantum client, whereas we just saw that what we want ideally is the client to be as weak as possible. Because if client is BQP, then it doesn't need to delegate this problem to the server because it can just solve the problem itself. So what we would like is the client to be as classical as possible. And so in this setting, the first protocol consisted of client which had quantum memories and a two-way quantum channel with the server. Then later in after 8 or 9 years, there was a really nice protocol, a couple of protocols by by Broadbent, Fitzsimons-Kashefi, and Harano, Bano, Rayban, where they consider a very weak quantum client. So basically here, the client only need to prepare single qubit states. So I'll go into detail of one of the protocol, which is this BFK protocol. And how does this work? Because this has been used in a lot of different ways over the time. And so in this protocol, we have a very weak quantum client who delegates the problem to a quantum server. And at the same time, this protocol achieves the blindness in information theoretic setting. So this is something that is not possible classically. So classically, we just saw that there is a impossibility result or unlikely consequences in complexity theory if you have information theoretic security for delegating NP-hard function. Whereas this protocol allows a very weak client to delegate any problem in BQP to a quantum server. At the same time, it is able to achieve this very high level of security. And so there have been a lot of progress in the later years on modifying this protocol, as well as trying to reduce the resources on client side. And so one such protocol is where a client is completely classical, and this is ideally what we would like. But this comes at the cost of two entangled servers. So the setting is there is a client Alice, and it communicates with two servers instead of one server. So now we have two server, maybe this is IBM, let's say, and this is Google. And moreover, the two servers are just not separated, but they have to be entangled. And so if you have a setup like this, where there are two servers who are entangled but non-communicating, then this paper by Raikard Unger he showed that how you can delegate using only a completely classical client, any problem in BQP. At the same time, they also showed how to verify that indeed the computation is performed by a quantum computer. So this is also a very nice protocol for testing quantum devices. So from complexity theory point of view, this goes under the class of MIP star. So MIP star stands for multiple interactive proof system. So we saw interactive proof system where we had one prover and one verifier, but multiple interactive proof system means that you have multiple provers and one verifier. And the star means that the provers are entangled but non-communicating. And so this is the class of problems that they show is equal to a QMIP. So basically a quantum multiple interactive proof system. So they showed that you actually don't require a quantum channel between Alice and Bob and Alice and Charlie. Instead, you can just remove this quantum channel entirely and still perform the same class of computation. And so this was a really amazing paper in that sense. And so far, there have been a lot of papers here which consider different ways of performing this delegated quantum computing, but it was not clear what is the amount of quantum communication you require in these protocols. And so what we did in 2013 is to show that the kind of protocols of these types are actually optimal. And so you cannot do better. So basically, we gave general techniques for lower and upper bounds on the amount of quantum communication that you would require to perform delegated quantum computation. And we also consider a lot of different scenarios for clients. So what if the client only has single qubit preparation systems? Maybe client could perform a general entangling operators and things like this. So I won't go into detail of this, but all I wanted to say with this is that basically there have been a characterization of the amount of quantum communication needed to achieve this delegation. But still, so far, all these protocols require quantum client, or even if we have a classical client, we require two entangled servers. So at least you require 2 quantum devices and a quantum channel. This is still not ideal because we don't have quantum channel exists very widely among all the people. So what we would like is a protocol where users can delegate computations over classical channel, which we are doing it over cloud, like using IBM and other cloud-based quantum computers, but we don't communicate over quantum channels. So in 2016, we actually gave a first scheme for a classical client and a single server. And in this scheme, we showed that client Alice is able to delegate very large class of computation. Yeah. So it's a large class of computation that she can delegate. And this other thing that we showed is that you can achieve information theoretic security, but basically we could only show that there is a, so basically we could only bound the mutual information between the client and the server. And so instead of perfect information theoretic security, we had a statistical security. So I'll also tell a bit more detail on this class of protocol. And then afterwards in 2017, there have been different results by Scott Aronson and other authors on limitations of achieving classical client single server delegated quantum computing. And so basically here we couldn't achieve the full class of computations, and we couldn't achieve perfect security. And so this paper turns out gives an oracle separation between the classes, which if you achieve BQP computations as well as perfect security, then this means that it's kind of unlikely. It's not a very strong unlikely result, but it's an oracle separation with some other assumptions. So we still don't know if it is possible to delegate quantum computations over classical channel with perfect security and with for like full class of quantum computations. And then so far till 2017, all the papers were considering information theoretic security. That means the server was completely unbounded, a malicious server. And then in 2018, we have protocols for quantum FHE, so basically fully homomorphic encryptions for quantum servers, for quantum circuits. Yeah, sorry. And then we also know that we can do classical verifications of quantum computations. That means a verifier who is completely classical can just interact with quantum server over a classical channel and verify any computations from BQP, like the class of quantum computations. However, this comes at the cost of computational security. But these protocols were really amazing in the sense that this was still not known, even computationally, this are possible or not. And so basically, these protocols are constructed from learning with errors assumptions. And so I'll probably go in maybe a bit of detail later on and show what kind of assumptions are needed for these. So, and then in last couple of years, we have also shown. So these were not modular in approach. So we have shown a delegated computing scheme over classical channel, which are modular. And we showed the limitations in security. Basically, these protocols were secure in standalone model, and we showed that there is some limitations if you go for composable securities and things like this. So again, this is something I'll cover a bit later, but I just wanted to mention that there are trade-offs between security and the amount of and basically the functionality that you could achieve over classical channels. So if you try to minimize resources a bit too much, then you have to give up some notions of stronger security. And then we also use similar kind of tricks to show a first protocol for quantum two-party computations, where there are two parties, Alice and Bob, who wants to collaborate over a classical channel, and they want to perform a joint quantum computation over their inputs. And so these are the kind of recent state of art in this field, and people have been more progressing over computational settings now. But information theoretic protocols are still an open problem in this. So maybe before going into detail, are there any questions so far? Okay, so if not, then I'll maybe just go into a bit more detail. So this was like a brief overview of where the field is and what are the recent results. So going into a bit more detail, I'll just, I guess you have seen the basics of quantum computing already in the workshop, but I'll quickly go through them just to make sure we follow the notation. So basically, the difference between classical and quantum computing, we have bits, and then the quantum analog are known as qubits or quantum bits. And so the gates, the analog of and, or, and not gates is the unitary quantum gates in the quantum. And the notion of reading the output bit in classical is generalized to measurements. So basic measurement is a function that takes a quantum state and outputs a classical bit. So I'm only talking about projective measurements here. So projective measurement is just, we can imagine this as some kind of function that takes in this psi and outputs m. And then I'll use these notations. So for Hadamard is basically this matrix. And similarly, these two qubit gates, C0 and CZ. And so CZ is the phase gate, which is symmetric, whereas C0 is the control NOT gates that, depending on the bit A here, it just flips the second bit. So depending on the control bit, it just flips the target bit. And so basically, the single qubit state will use the Dirac notation. And then from 0, 1, we also have superpositions of states, alpha 0 and beta 1, where alpha and beta could be from complex numbers. And similarly, we could denote n qubit states as a superposition of this alpha x. And so x is an n-bit string, and where the condition is that the mod square alpha x is sum up to ones for to satisfy the probability. And this is an example of a simple 2-qubit circuit where this is initialized in zero states, and then we have applied Hadamard on the first qubit, applied a control node, and then we get an output state. And basically, this is a very well-known circuit to prepare entangled state. So maybe this is a very simple exercise to check that this does indeed produces an entangled state in the end. So this was just to set up the notations, and this is something that I guess maybe not all the people have heard about it. So we all have been very familiar with the quantum circuit model. That is basically prepare a quantum state in the computational basis. 0 or 1 is the computational basis. So prepare a quantum state, then apply a sequence of unitary operations that are analog to the circuit model, like classical circuit model. And then we just perform measurements in the end for 1 or more qubits to get our desired output. But there is another computational model in quantum which doesn't have a direct analog in the classical computing, which is this measurement-based model for quantum computation. And in this model, we don't perform unitary operations. Whereas what we do is we take, so the computation is driven by single qubit projective measurements instead of unitary operations. And so the evolution is done by measurements, and that basically drives the quantum information. But for that, we need to start with a highly entangled state. So instead of starting with the separable state and computational basis state, we start with a multi-qubit entangled state, which is for compactness. We denote it with a graph. So basically, all these qubits are in the plus state. So if I have to write these 2 qubits and a CZ, this is plus state, and this is a controlled phase operation which entangles these plus states. And so if you have to write this like 5 by 5, which is 25 qubit state, then it will probably take this whole slide to write this state. Whereas we usually use these graphs to denote compactly the state of the system. And so and this Pac-Man is just a pictorial way to depict single qubit measurements. So because we are not performing unitary operations, and apparently this is enough to perform any quantum computation. So basically, all we need is a highly entangled state to start with, and we need to perform this single qubit projective measurements, which have to be adaptive, which I'll just tell in a moment. What do I mean by adaptive measurements? But these have to be projective measurements are enough for this. And so this might seem like a very strange model because we are not performing any unitary evolutions, and yet we are getting our desired computation. But basically, a very nice analogy that I like to think of this is the circuit model is kind of making a sculpture where you add stone by stone. Whereas on the other hand, you could equivalently get the same sculpture if you start with a huge rock and start carving out. And so this carving out is the kind of operation that I think is like a single qubit projective measurement because it's destroying the state. And at the same time, if you're careful enough, you can actually get the same sculpture from both the methods. And so both the methods are equivalently powerful. Maybe you require a much bigger rock compared to this. So resources wise, this is costly. But maybe you have a rock which you get it for free. Then they are equivalent in power. So in power, by power, I mean they are equivalent in terms of kind of computations that you do. So from both the model, you could perform BQP computations. And so this model has been particularly useful in delegation protocols. And so that's why I've been trying to introduce this model now. And so basically, we can also think as some recipe for MBQC is like you prepare. So basically, instead of taking this huge rock, we could actually just prepare the huge rock. And to do this, we just take each qubit in plus state and apply these control phase states. And then we know that measurements are enough. So single qubit measurements are enough. And this is the adaptiveness that I was talking before. So basically, just the single qubit projective measurement is not enough. But what we need to do is, if I have this graph state, and if I have performed measurement of this, let's say I got a measurement outcome M1, and then if I perform a measurement on this, then I need to be a bit careful on what is the measurement outcome I got, because I cannot just blindly perform measurement in any basis here. This basis could depend on the measurement outcome here. So this is what I mean by adaptive. So basically, the choice of measurements of future qubits depend on the measurements that have already been performed before. And in this way, you cannot parallelize this circuit in just depth 1. So you need a minimum depth of computation here. And so for this talk, I'll only consider. So you could imagine preparing different kinds of resources for different kinds of computations. But in this talk, I'll only consider resources which are generic, which is like this square cluster state. And so basically, the square cluster state and measurements in XY plane of block sphere, actually this is enough to perform any computations, any universal quantum computation, as long as the measurements are adaptive. And so maybe that's the only important thing that we need to remember in this model. And so just to give you a quick idea, how does this computation translates into a circuit model is using this trick called one-bit teleportation. And this is just the essential idea to simulate the simple circuit identities. For example, let's take a very simple graph, which is 2-qubit graph. And so the first qubit, we have this state psi, which is in this alpha 0 plus beta 1. And this is CZ gate. So CZ basically is just this. And so if you try to compute this circuit, basically you take psi plus and you apply CZ, and then all the measurements, like I said before, are in XY or XY plane measurements. So basically XY plane measurements are just some, if I have a XY plane measurement with angle theta, then basically that just means that I'll perform RZ of theta, a rotation around Z axis. I'll apply a Hadamard, and I'll perform a computational basis measurement. So this is what I mean by an XY plane measurement. And so here I'm performing an XY plane measurement with angle 0. That means there is no RZ. And so all I'm doing is a Hadamard and a computational basis measurement. And so once you perform this measurement, the state that you get here is another exercise to check is you'll get a state that is Hadamard applied to the initial state and some Pauli byproduct. And so basically this state as if has been teleported to the next qubit. And that's why this is also known as one-bit teleportation. So this is a bit different from the usual teleportation circuit. But basically what you do is you keep on teleporting the psi from one qubit to another. And then if you do this enough, then you keep on getting this Hadamard and RZ in front of this. And so basically using this gate teleportation trick, you can get any universal quantum computation. And so maybe just to see a bit more, let's say instead of 0, now we change the angle to theta. So like I said, this just means that you have applied RZ of theta and Hadamard before the measurements. And so what this means is that instead of just teleporting H, now you have this U, which has been teleported along with the state psi. And to see this is very simple because we have this psi plus, and then this is RZ of theta. This is Hadamard. And so basically RZ of theta commutes with because RZ of theta is also diagonal in the computational basis, and CZ is also diagonal. And so RZ of theta commutes with the CZ. So basically I can remove RZ of theta here and I can write it here. And now this becomes my new state psi prime. And so here, this means that I'm just teleporting this psi prime with H of theta. And so basically I would have this psi prime here, and this is the psi prime. So you could see that why performing with the angle theta, you get this is RZ of theta psi because of this commutation rule. And so we can even go further from 2 qubit, we can see what happens with the 3 qubits. And so if you have 3 qubits, you have this graph, this is this, and then you have this measurements in XY plane with angle alpha 1 and alpha 2, and which means that you are performing RZ of alpha 1 and Hadamard, and the second is RZ of alpha 2 and Hadamard, and there is a plus minus 1 here. This is because depending on the measurement outcome, you have to adapt the angle here. And so that's why you have this adaptiveness here. And so if you obtain an outcome 1, then you actually use a minus alpha 2. Whereas if you get an outcome 0, then you don't have to change the angle. And this is just to correct this poly byproduct, because otherwise you'll keep on getting this byproduct, which you don't want it. And this will just create errors in the computation. So if you want determinism, you essentially have to remove these poly byproducts. And this you can remove it by changing the basis of the measurements. And so going a bit further, you could also do 2-qubit circuits. And this, I'll leave it as an exercise. So you could see the simple 10-qubit graph state where you have inputs here and you get outputs here. And so basically, this is as if I've applied a unitary U, which is represented as this on an input and output. And so you can go on and on for any number of qubits, and essentially you can get any n-qubit circuit using measurement-based quantum computation. And so just the important points to remember is that in MBQC, you only need adaptive single qubit measurements. And moreover, this is computationally equivalent to the circuit model. So in this talk, I'll only consider MBQC model of computation. And maybe a couple of more things from basics of quantum is, like, one of the main theorem is no cloning theorem. And what does this say is that there cannot exist any physical device that can output 2 perfectly identical copies of an unknown state psi when given a single copy of psi. So basically, we cannot have this black box which takes psi and some other state phi and outputs 2 copies of psi. And this unknown quantum state is important. So if this psi is known to if there's a classical description inside this cloner of this psi, then you can always copy it. So this only applies to unknown quantum states. And one has to be very careful in applying no cloning theorems, because usually you kind of fail this condition. So this has been useful in a lot of ways. So one is to show security in quantum key distributions. This is also very useful in quantum money protocols and other cryptographic protocols. And a bit surprisingly, this has also been recently used to prove some security limitations. So this, we use it like no cloning theorem to prove that you cannot achieve delegated quantum computations over classical channel with some notion of security. And similarly, we also show similar kind of limitations in 2-party quantum cryptographic primitives. So this is a very nice tool, not just to prove what kind of security is achievable, but also what kind of security you cannot achieve. And so again, another basic primitive to go over is quantum teleportation. So in this, the setup is we have 2 parties, Alice and Bob. So the reason I said quantum no cloning is, I'll again come back to it later on, but so maybe these might look like different steps at this point, but I'll try to connect all of them in the end. So for quantum teleportation, we know that there are 2 parties, Alice and Bob, and they share bell pair between them. And Alice has an unknown quantum state psi that she wants to teleport it to Bob. But she doesn't share any other quantum channel between them. So the way to proceed is Alice would take this state psi and take 1/2 of the bell pair. And then she would apply this circuit, which is the same circuit as we saw before. It's the control node applied with Hadamard. And then she performs a computational basis measurement. So this is also known as bell basis measurement. And so basically projecting into one of the bell states, she gets 2 classical bits, A and B. And on the other hand, if we look at what is the state that Bob gets, so Bob gets a state psi here, which is encrypted with the key A and B. And so unless Alice communicates A and B, Bob has no information about the state psi. Because if he had some information about psi without classical communication, then this would allow faster than, so this would allow superluminal signaling. So yeah. So to prevent signaling, we know that Bob has no information about this psi before any communication about A and B. And once Bob gets A and B, we know what are the steps to recover this psi. So basically, this is a decoder. And this decoding operation is very simple since we know that teleportation only gives poly byproducts. So Bob could apply just the poly operations. So I won't go into detail of this, but this is also very easy to verify that Bob can get this psi A0 plus beta 1 very easily. Okay, so maybe let's look at what is this state at this stage before Bob gets this A and B. So this is the state, like I said, it's a poly control with the bits A and B with the psi. And maybe looking a bit more in detail, the density matrix corresponding to this is just this simple ZAXP applied to the psi. And if you sum over A and B, so summing over A and B means that Bob has no information about A and B. So that means you just trace over AB from this state, and you can verify that what you get is a completely mixed state. And this proves that there is no information that has been sent from Alice to Bob about the state. And in the end, Bob recovers the state psi. But this doesn't violate no cloning theorem, because once Bob gets the state psi, Alice has no longer this state psi on her side. So there is never two copies of state psi at any point of time in this protocol. And why are we talking about teleportation is because it's also very much related to something in cryptography that we call one-time pad, or like quantum one-time pad. And basically, a quantum one-time pad is a scheme where Alice has some bit M that she wants to send it to Bob over an authenticated channel. But there is an eavesdropper here. So if Alice sends this message M directly to Bob, then Eve would be able to know what is this message M. So a very simple scheme to hide this message M from Eve is we just pad it with some random key R, and Alice and Bob share this R ahead of the time. So if Alice one-time pads this message M with this randomness R, and Bob knows the R, so he again one-time pads this message R, then we get message M back on Bob's side. And so this is a very easy way to securely communicate between Alice and Bob if they share this key ahead of the time. And so Eve has no knowledge of message M because this message M is perfectly hidden from Eve because of this randomness R. And so this is a very well-known technique in classical cryptography. And so there is an equivalent technique in quantum, which is also known as quantum one-time pad. And here, instead of classical message, Alice wants to send this message M, this message psi, which is a quantum state. So one way to achieve this is Alice, instead of XORing with R, Alice applies this poly encryption, which is this. So they share the key A and B. Now they share 2 bits instead of 1 bit. And then Alice just applies this poly Z and poly X that are controlled over this bits A and B. And since Bob knows the same bits A and B, Bob could again apply CA and XP. And because of poly commutation rules and identities, we know that this is identity with some phase. And so basically, Bob would be able to recover the state psi, whereas Eve, we just showed that Eve only sees this state psi. And since Eve doesn't know this A and B, this is exactly the same proof that we can use to show that Eve has no information about state psi if he doesn't know the key A and B. And so basically, you could see there's a relation between teleportation and quantum one-time pad, which is that that if this classical communication is already shared between Alice and Bob, then Alice can just securely communicate with Bob for any quantum messages. And so basically, Bob can read the message, and Eve gains no information, and the proof is same as this. And now, another way to see this is that why do we use this poly one-time pads? Is because
excuse me, your presentation is not visible. What you are doing on your screen, only your face is coming over here.
Oh,
maybe you have not shared that.
Oh, is it
No,
also same for?
No, it's visible to me. What about the rest of the participants? The
Sir,
screen is
it is
visible.
visible, sir. It is visible, sir.
Visible
Sir,
to
it is
everyone.
not
Because
visible, sir.
more than 60 are
Sir, it's
attending.
visible, sir. Sir, screen is visible.
For some of you, if it's
As
not
quantum
visible, then
one-time pad.
rejoin once again.
Okay.
Okay, you can
Okay,
carry on.
Yeah, okay. Yeah, please let me know if at some point if it's not visible to like more than a couple of people. Yeah, okay. So basically, this is the same quantum one-time pad scheme, and we could also use. We could see why this is similar to a classical one-time pad, because a classical one-time pad is just encoding or like sending the messages in one basis, whereas in quantum states, what we want to do is we want to hide messages in both the bases. And so basically, we know that quantum one-time pad is just, so classical one-time pad is just the bit flip. Whereas if you do the bit flip in both the bases in X and Z, then you get basically a full encryption of a quantum state. And so that is the reason that we did this poly encryption, and this was sufficient to hide the full state. I'm sorry. Yeah, okay. So I won't go into like a lot of details of this, but basically now I'll use this simple cryptographic task to construct a complex delegation schemes. And I'll talk about different kinds of delegation schemes. So maybe before this, are there any questions so far? Okay, so if not, then I'll just go into detail of one of the well-known delegation scheme, which is this broadband Fitzsimons-Kashiffi scheme. This is also known as blind quantum computation. And I'll just call it BFK scheme. And this was the 2009 scheme. And there have been, so the scheme has been, has a lot of variants now for like device independent setting, or the optimality have been considered, or it has also been implemented in experiments. There is a fault tolerant version and things like this. And that's why I think this is a very nice scheme to know. And also this has been used in a lot of new results recently. So in this scheme, we have Alice, whose computation, so the scheme is based on MBQC model. So this measurement-based quantum computing model. And also this is interactive. So basically Alice has a small quantum device. So by small quantum device, I mean she has the ability to prepare this single qubit state psi tilde. But note that just preparing the single qubit state doesn't mean that Alice could perform all the universal quantum computation, because she needs entangling gates and she needs measurement devices, which she doesn't have. So she needs the help of a quantum Bob. So Bob has a quantum computer, And Alice's computation, instead of writing it as unitary, I would write it as a graph and some measurement angle. And we just showed that this is equivalent to any unitary because they are like equivalent. So MBQC is also as powerful as a circuit model. So from now on, I'll write this Alice's computation with graph and these angles, and this graph has this size n times m. So basically, so this blue line is basically Alice sending this single qubit state. So Alice prepares this n times m single qubit states and sends it to Bob. And all the states are parameterized with this angle theta. So she has this lot of thetas that she just randomly chooses from this set k pi over 4, where k is from 1 to 8. So basically, this is just the pi over 4, 0, pi over 2, so on. And once she chooses this theta, she prepares this quantum states, and then she sends it to Bob. And so Bob prepares this graph state because Bob has, like I said, Bob has a universal quantum computer. And then Alice uses this theta, and using this angle alpha, she prepares this angle delta, which is theta plus alpha. So for each node, she prepares this angle delta I and sends it to Bob. Bob uses this angle delta I and performs a measurement. So remember, in MBQC, Bob only needs measurement angle to perform the computation. So Bob performs the measurement in this basis delta I and obtains an output, this 1 bit. And then Bob sends this 1 bit to Alice. And then Alice uses this 1 bit and this again theta I plus 1 and angle alpha I plus 1. And using this bit B, she computes the angle delta I plus 1. And then this goes on for each I. So she keeps on updating her classical measurement angle, and then she sends it to Bob. So note that after sending the state, all she needs is this classical computer to update this angle. She doesn't need any more quantum power. So basically, so we can see for a simple example, like for the 7 qubit. Let's say Alice wants to compute the 7 qubit computation over a cloud quantum computer. So Alice sends, so note that the computation that she wants to perform is all plus states, and she wants to measure this in some phi 1 angles. Let's say her computation is parameterized by this. So if she has a quantum computer, she could just prepare this graph. So this is the graph. And then she can just perform this measurement in phi 1 basis, and then she gets the output. And this is her target computation. But she doesn't have quantum computer, so she cannot send this phi directly to Bob, because sending this phi means that Bob knows what is the computation that Alice is performing. So Alice wants to hide this. So to hide this, note that this is just the same identity. Instead of writing phi here, now I'm writing this RZ of phi and Hadamard. So this is XY plane measurement. So basically, this is the circuit that Alice wants to implement without actually sending phi 1 to Bob. So how can we perform this kind of circuit in a delegated manner? Is Alice, instead of phi, she adds an angle theta 1 here, and she adds an angle theta 1 here. This is the same circuit as before. And why this is true is because RZ theta commutes with this control Z. And so basically, this thing is still equivalent to RZ of phi 1. So this is nothing, but I just divided it in 2 different ways. And then she equivalently write another circuit where she just applies Z which depends on this random bit R1. So this R1 is a random bit. So writing ZR1 here equivalently means I could just decrypt with R1 in the end, because now my measurements have been one-time padded. So one can just check that writing ZR1 here and applying a bit R1 here just cancels them. So this cancels with this, and theta1 cancels with theta1. So the computation is still with phi1. So there has been no change in the computation. I'm just equivalently writing the circuits in different ways. And now basically this RZ of theta1 plus R1, I just write it here. So I just write this plus theta R1 is on plus state. This is just the shorthand notation. And now you see that if Alice can prepare these states where theta1 and R1 is a random state, then this could be a quantum Bob. So basically Bob performs these entangling operations, and this delta 1 is exactly the angle that was here, phi1 minus theta1. So instead of sending phi1, now I'll be sending delta 1, because I've already applied a random operation on my plus state. So I could again apply some randomness and decrypt the randomness that I already applied before. But to Bob, this delta 1 looks completely random because Bob doesn't know theta 1. So he cannot guess anything about phi1. And the measurement outcomes doesn't leak anything about B1, because measurement outcomes are one-time padded with R1. And so if you do this simple trick actually allows you to do delegated quantum computation in an information theoretic way, because all these are one-time pads, and this is just a quantum one-time pad for plus state. And so the resources that Alice used, so this is Alice's lab. This is Alice's lab. And this is Bob's lab. And maybe you could assume that these are very far apart. So all the requirement on Alice's side is this single qubit measurement states, ability to perform these poly operations. Sorry. However, she doesn't have power to entangle or Hadamard. This is all on the side of Bob's side. And we are assuming that Bob has universal quantum computer, so he can apply all these operations. He has a quantum memory to store this huge graph state, and he can perform all these quantum operations and measurements. So all this protocol require is a one-way quantum channel at the first step to send all these qubits to Bob. And then all we require is to just interact with Bob with this delta and get this B1. And so you could see that this protocol would lead to a correct protocol, because we have just equivalently wrote the circuits and we have not changed the actual computation. However, we have just restructured the computation such that Alice is able to hide the essential parts of the computation now from Bob. So to prove security, like we said, this is also known as blindness. So what we want to show is that Bob is not able to guess anything about client's computation. And client's computation is essentially parameterized by these angles phi1. So informally, we want to say that Bob cannot guess anything about phi1. However, this is more formally defined as the statement where we say that, okay, a protocol P on this input X, this is input X, doesn't leak anything except this L of X, which is the distribution that is before and after the computation. And so that the information is fixed and it only depends on this L of X and nothing more. And so to show this theorem, this is not a very hard proof. So basically these are all the information that Bob receives. This is Bob's information. And basically you can see that since Bob doesn't know Ri, we would sum over Ri here. And you could show that if you sum over Ri over the state psi I, you get identity over R2. So you get a completely mixed state. And basically, if it's a completely mixed state, that means Bob has no information about the theta. And if this theta is completely random, then you could also say that Bob has no information about this phi, because this delta is like classical one-time pad of this. And so since we know that classical one-time pad and this quantum one-time pad are information theoretically secure, so we have shown security against an unbounded Bob. So that's why this protocol is also information theoretically secure. That's the highest level of security we could imagine. However, note that Bob does know some information about the protocol. And what is that information? That is this dimension of this resource state. So basically, Bob knows that I have, as a client, I've sent him n times m quantum states. So he knows this n and m, which is basically the circuit dimensions. Like I said, this graph has this dimension n and m. And this is inevitable because any server, he would know what is the kind of resources that has been used by them over the time. So this cannot be hidden from any server over cloud. You could pad it, but you would not be able to hide an upper bound on it. So this is not an actual leakage of information. And so this protocol is really nice in this sense that you get the best level of security. And so I'll quickly go through some. By the way, is there any question in this protocol? And so okay. So another easier version of this protocol is if instead of, so in the previous protocol, the client had ability to prepare the single qubit state psi, which is this state. However, if the client doesn't have ability to prepare this, but has ability to perform measurements, then can we perform delegated quantum computation? And this was later on shown by Morimae Fuji, that this is very simple protocol in the sense that server prepares this graph state. So maybe client tells that maybe prepare n times m graph state, right, which is this square graph state. So server prepares the graph state and sends qubit by qubit to client. And since client has ability to perform this single qubit measurement, then this is essentially just the MBQC model. And from MBQC, we know that client would be able to get the correct computation at the end. And it also trivially achieves blindness because there is no information that goes from client to server about this measurement angles phi 1. So this, in this sense, this is a very simple protocol to achieve delegation if the client has ability to perform measurements in XY plane. And this also achieves information theoretic security. And the third setting that we saw before was by this Raikard Ungar-Wazirani, where the client was completely classical, and it was delegating this to two servers, server 1 and server 2. And so this is a completely classical client. So now client doesn't have ability to prepare quantum state or ability to measure quantum state. However, the server shares this EPR pair, a lot of EPR pairs, basically. And another condition that is that the server should not be able to communicate. So they should not communicate during the protocol. So assuming these conditions that server shares the EPR pair and don't communicate, they show a protocol where a classical client could delegate any quantum computation. And basically this works in the following way. So assume that server 1 and server 2 shares this psi minus, which is EPR pair. So maybe this is on server 1 and this is on server 2 side. And then client instructs server 1 to perform this RZ of theta and Hadamard and measurement. So basically this is the same measurement as we saw in the 1-bit teleportation. And from that circuit, we know that this has to be equal to this. So essentially what we, maybe it's the other way now. So essentially what we are getting is we are using a classical client to somehow control one of the server to prepare state on the other server side without knowing this theta. So since they are not communicating, server 2 doesn't know what is the theta that Alice told server 1 to perform measurement in. And so basically server 2 has a lot of plus theta states in his side without actually knowing theta. So this is equivalent to client sending this plus theta to server 2, but just that now she's using the help of server 1 to do this. And so they showed that you could delegate the computation in this manner. Moreover, they showed much stronger properties that the classical client actually can verify that server 1 and server 2 are performing the correct computation. And so basically this protocol also allows us to do verification of quantum devices. So client can verify that server 1 and server 2 are indeed sharing EPR pair and are indeed performing these sets of operations. Yeah. Okay, so again, I guess I'm probably not going to go into detail of this, but yeah. So far what we have seen is that we have seen 3 protocols, and the power of client is in the first case preparing single qubit states, in the second case measuring single qubits, and in the third case it's completely classical, but at the cost of having 2 servers that are entangled but not communicating. So a common feature is that you need at least 2 quantum processors, which is not ideal. And so basically the main question is, can we have a classical client and a single quantum server delegation scheme that also achieves information theoretic security? So all these protocols are information theoretically secure. That means they are secure against an unbounded server. And so this is still a major open problem. There are some unlikely, there are some implausible results, but there is no strong impossible results, or there is no strong possible results. There are some slightly possible results in this direction. And so one of them is, so this is the same question that I said, is it possible to perform this blind quantum computation with a completely classical client and a single quantum server? And so one of the protocol to do this is using this classically driven blind quantum computing protocol. This is also based on measurement-based quantum computing. However, in this, there is a completely classical channel here. So client has no ability to prepare this plus theta state that she was doing it before. And so as this is, I'm probably not going into details of this, but the idea is we again describe client's computation with this graph and some angles and this flow bits. So these flow bits are just the poly byproducts that we need to keep track of. So like I said before, the measurements are adaptive. So we need to keep track whether this qubit needs to be adapted based on measurement outcome of this or measurement outcome of this. So depending on what measurement outcomes we adapt, based on what measurement outcomes we adapt, the computation would be different. And so these flow bits are also important in that sense. And so basically the high level idea is we would use this flow bits and hide it from the server. And so server doesn't know whether the client adapted this basis for this alpha, let's say, alpha j, if this alpha j was adapted based on B1 or B2. And so since the server doesn't know, only the client knows, they are completely different computations. And so this is a super simple protocol where Alice sends the angle alpha prime where the angle alpha is the actual computation, and alpha prime is basically just the first one is just alpha plus r pi. So this is not hiding the angle perfectly, but it's hiding one bit of it. And so basically Bob performs this measurement in plus minus alpha prime basis, obtains a bit B1 or B prime, and sends it to sends it to Alice. Alice uses this B prime, uses this randomness R, and these are the flow bits F. And he uses this F to compute this alpha prime, the next one, which now depends on this F and depends on this R. And so based on, since server doesn't know this flow bits, basically server doesn't know some part of the angle alpha prime. And so using this kind of idea, we show that you can actually perform classical client cloud quantum computing scheme with a single server in information theoretic setting. However, and this is also based on the same model of computation. And sorry. And so basically this was shown in like 2017, and it's also the first scheme with a classical user and quantum server where the server is unbounded. So there is no mathematical hardness assumptions that is needed to achieve the security. And the main idea is we are using an algorithm that is this flow algorithm to ensure security. And another important thing is that there is no quantum devices needed, and there is no overhead in terms of number of qubits required for this scheme on user side, which is very nice in terms of practical settings. And so basically, I won't go into details of security. However, I'll just show the brief idea that let's just take this 4-qubit cluster state, which Alice wants to delegate to the server. And so what she can do is, let's say the computation that Alice wants to perform is given by this angles alpha, beta, gamma, delta for this 4 qubits. And the order of measurement is known to both Alice and Bob. That means Bob knows that Alice would send this qubit first, and this qubit second, and this qubit third, and this qubit fourth. And this is the measurement that Bob would perform. And so this is, from Alice's point of view, this is the computation that she wants to perform. However, from Bob's point of view, there are 9 equivalent computations that are possible. And why 9 and why not just 1 is because of the fact that Bob doesn't know whether this second qubit is adapted based on the first qubit or the third qubit. For example, this red arrow means that I've adapted this angle beta based on B1. Whereas this beta is not adapted based on B1. And instead, this angle gamma is adapted based on B1. So depending on how I'm adapting my measurement angles on Alice's side, the computation is driven in a different way. And this is actually also this 1-bit teleportation circuit. So if this is computation psi, if I'm teleporting on this qubit or if I'm teleporting on this qubit. So this is another essential way of looking at this protocol. And this is only known to Alice. This is not known to Bob because Bob is performing a generic computation. So from Bob's point of view, there are 9 computations that are possible, whereas Alice's point of view is only 1. So what we did is we generalized this protocol. So we generalized this to an n by m cluster state and found out that the number of possible computations are actually exponential. So this number of possible computations is exponential with this exponent. And this means that Bob has no idea which of these exponential computations that Alice is performing. So this is some level of security, but to formally define it, we had to actually compute the mutual information between Alice and Bob. And we showed that this is bounded. However, this is not a perfectly secure system because Bob still knows some information about angles. It's just that he doesn't know all the information. So this is not a perfectly secure scheme. Moreover, we couldn't show that you could compute any computation from BQP. We showed that you could compute from a very large class of computation, but this is still an open problem whether if you could do a full universal set of computation with this idea of flow ambiguity. And we are also implementing this in experiments. So this would be like a first experimental demonstration for secure cloud quantum computing over classical channels. And so, so far, all the experimental demonstrations have been done with at least 2 quantum devices. So this is so far the most practical implementation. And we are actually implementing this exact same computation, that 4-qubit, using photonics in like a group of Philip Walter. So yeah, so the main point from this takeaway from this slide is that these schemes are not just theoretical schemes, but one could also try to push it to a bit of experimental settings and try to see what kind of computations you could quantify and what kind of securities we could push it to. So yeah, any questions so far?
So participants, anybody having any questions, you can ask.
I see a hand.
Yeah, Gurvinder Singh. So you can unmute and you can ask.
Okay, am I audible, sir?
Yeah, sure. Go ahead.
Yeah.
Sir, my question is there any simulator that we can use to experiment the different encryption techniques in case of the quantum computing lab?
Yeah, so I mean, so there are a lot of these cloud-based quantum computers that we can use it over internet. So for example, we can access IBM scheme and things like this. But the thing is, all these protocols are interactive, and IBM or any other cloud-based services, they don't allow interaction. So they only allow non-interactive schemes. So you have to tell them in one setting what are the computations that you want to perform, and that's why it's not clear how we will be able to implement this on a simulator. But you could always write a program where you could imagine Alice and Bob are spatially separated, and this you could do it interactively then. So you could write a quantum simulator for this. But okay, experimentally, this is hard to implement it at this point with the cloud-based computers because they don't allow this adaptive measurements, and they don't allow interaction, and that is the reason it's very hard to implement these over any of the cloud-based IBM or Rigetti or something. So we don't know how to do interactive protocols over them.
Okay. Actually, I want to compare the results with the classical version and the quantum version related with the cryptography algorithms.
Yeah. So I'll tell you, like there is a quantum FHE, which is basically a quantum fully homomorphic encryption scheme that is based on learning with errors. And that protocol is non-interactive. So in principle, you should be able to implement that protocol over cloud computers. But the point is, this protocol has a very high overhead. So that means you would need 500 to 1,000 qubits to implement a very small, circuit over 2 or 3 qubits. And that we don't have it so far. So the problem with them is is the overhead is very high. So if we can reduce the overhead of this fully homomorphic encryption schemes, we could implement it. So I guess classically you could implement FHE because we know how to run programs over 1,000 bits and security and stuff like this. But quantumly, we don't have that many qubits with us. So I mean, at this point, does that answer your question?
Yes, sir, definitely. Thank you, sir.
Okay, so I guess
Yeah, I have one question, Atul sir.
yeah, sure.
Because we have existing cloud quantum servers from IBM, Google, and all, but as far as measurement-based schemes are concerned, on which you are working right now, so how you have implemented this as far as the working of secure cloud computing is concerned? Because as you mentioned that interactive is totally absent with the existing cloud, or you have to take permission from them. But how you are implementing this graph-based and other schemes, especially based on measurement one?
Yeah, so basically we have not implemented with cloud-based services. So we have implemented in an experimental lab.
Okay.
And so in this lab is like, so this is photonic system, whereas so in photonics, this is a very good physical system to implement MBQC.
Okay.
But superconducting systems, we don't know how to prepare. Like those are not suitable for MBQC. Those are very suitable for circuit model. So to do MBQC, you'll have to go via the route of circuit model even in them. And so I mean, we could implement this in labs, but we don't know
Okay.
how to implement it in practical services so far. So this is still a lab setup. Like this is going in like a 20 by 20 meter lab, basically,
Okay.
something like that. Yeah.
Okay.
So this is just a tabletop experiment. Yeah.
Yeah, that's a wonderful work. Anybody having any queries? Because already 12:47, as I observe from the screen of Atul sir, it's already 12:47 a.m. So if you
Yeah.
have any queries, so Atul, look, please introduce yourself, because I have forgotten to introduce because many have joined late. So
Oh,
Atul
okay.
is actually from University of Maryland. Okay, Atul, you can continue for half a minute.
Yeah, I mean, I can introduce in the end as well. So I'll maybe just take like 5 more minutes or something.
Yeah.
I think I had way too much prepared, but I can just, so I won't go into the next part in detail, but I'll just skip it. So basically the next part I wanted to cover was all the protocols that we saw so far before had like quantum channel in it, or this classical scheme that we saw had a problem with security, basically that it was not perfectly secure, or it was not, so it's not constructive in that sense. So is there other ways to dequantize this quantum interaction that we saw in this BFK scheme and obtain a delegated quantum computing scheme? And so for this, I won't go into detail. Basically, we use a cryptographic primitive known as remote state preparation. This is exactly like simulating the quantum channel over classical channel. And basically, one way to obtain this black box, so this is a black box that we want. And basically what this black box does is it gives classical bits A and B to Alice, and it produces a quantum state to Bob. And now we want to find out how to produce this kind of box. So, it's very trivial to see this box. We could use quantum teleportation to achieve this box. Like if this is some state psi, which is encrypted with poly, then Alice and Bob could share EPR pair, and Alice could just perform measurements. And then Bob gets this encrypted state. And similarly, Alice could just prepare the state that she was doing in the previous protocols, and she could just send it over quantum channel. So basically, if we have quantum channel between Alice and Bob, this is very easy to instantiate. However, we don't know how to instantiate this with classical channel. And basically, with information theoretic security from Bob's side, this is impossible. So what we do is we use a protocol for RSP over classical channel, but that is only computationally secure. And so basically, that computational security comes from these classical cryptographic functions known as either trapdoor claw-free functions, or they are known as like homomorphic trapdoor injective one-way functions. So these are like cryptographic functions which are hard to convert, but they are one-way, and they are injective. That means they are like one-to-one functions. And so these are like mathematically hard functions where the essential property is that they have a trapdoor. So Alice has a trapdoor that Bob doesn't know about. And now we are leveraging on this trapdoor to somehow encrypt quantum systems on Bob's side that Bob cannot decrypt because Bob doesn't have this key. So now we are using classical cryptography to enable quantum cryptography over classical channels. And so this idea has been used a lot in last 2 or 3 years. And this is basically started with this works of Mahadev on this classical homomorphic scheme for quantum circuits, and basically by this Brakersky et al., and also in parallel work by Kojokari et al. And so we use this scheme to construct a delegation scheme. So, and I won't go into like this because of shortage of time, but so this uses a standard quantum algorithm protocol to prepare from Alice's side a quantum state on Bob's side using only classical channel. But it's encrypted with the keys that are only hidden as long as Bob cannot solve, as long as Bob cannot solve some mathematically hard problem, which are, for example, learning with errors and stuff like this. And so basically we use this in 2 applications. One is this delegated quantum computation. So we use this remote state preparation to remove the quantum channel from this BFK scheme that I mentioned in detail before. And once we remove the quantum channel from BFK scheme, the overall scheme becomes completely classical. So Alice and Bob now only needs classical channel, but still you have interaction in between them. And this is still only computationally secure. So this classical channel comes at the cost of computational security. And there are these cryptographic assumptions. So assuming these things, we showed that one can have a completely classical delegated scheme, which is modular. Moreover, we studied what are the trade-offs between the different notions of security. And so we showed that composable security is not achievable in this setting. And so this impossibility came from this no cloning argument. And this is where we use no cloning in a impossibility result instead of possibility. And so application 2 was we gave a first quantum 2-party computation over classical channels. So quantum 2-party computation is we have 2 parties, Alice and Bob. So now both the parties have input. So in the previous scheme, only Alice has input and Alice had output. Now both the parties want to collaborate. So Bob has an input psi and Alice has an input f. And let's say Alice wants to obtain an output f of psi. And so this is very essential. This is basically, if you generalize this, then you get multi-party computing, so MPC or secure MPC. And so we showed that you could achieve quantum 2-party computation where Alice and Bob only share classical channel. And so this again brings the practical relevance of these protocols. And here also we showed some trade-offs between security achievable in different notions of simulation-based securities. And also we showed that Mahadev's protocol for this classical verification can be turned into something called zero knowledge and proof of quantum knowledge and stuff like this, just with classical verifiers. So basically all I wanted to say is that this remote state preparation essentially turns out to be quite useful in turning protocols or in constructing protocols for quantum cryptography over classical channels. And maybe the last segment was on verification of quantum devices. And so far we were only concerned with the privacy aspect that means we wanted to hide the computation from Bob. But can we also trust the results produced by computers, quantum computers? And this goes back to the initial statement that I made, that quantum computers are not simulable by classical computers, or at least we believe that. So how we will be able to predict the outcomes that quantum computers will give us? And so this is a question that is not just relevant from practical point of view, but it's also a very foundational question. And just to give you some relevance in practice, so this recent quantum supremacy and advantage paper by USTC China, so I took this paragraph from Scott Aronson's blog, where he was, so that paper was accepted in Science, and he was one of the reviewers of this paper. And basically he told them to verify the outcomes of the quantum computer. And so basically, just to verify those results, which were like for 40 qubits, it took them like around 300 crore Indian rupees worth of supercomputing time. And so since the verification process was not efficient, they had to simulate it over the quantum computation over supercomputers. And so this lack of efficient schemes for verifying quantum computers just for 40 qubits lead to such an expensive referee report. So you could imagine this relevance of having efficient schemes for larger would be very important. So we need solutions that go beyond brute force classical simulations. We don't want to just simulate it on supercomputers, because we want to go beyond n equals to 40 qubits very soon. And so basically, the point is, you could use this delegated quantum computing schemes to also verify quantum computers. And so basically, you could just introduce traps in it. Since server doesn't know what computation he's performing, if you introduce a trap in it, and if server deviates, then he would be detected with very high probability. And this is the kind of idea you could use to verify a quantum computer from performing or deviating. So if a server is trying to deviate, he would be detected with very high probability, because he doesn't know whether this is a trap or this is a trap. So he would have to behave honestly at every step. And so this is a very high level idea of a very complex argument, but this requires quantum verifier, because we know that these schemes have a quantum client. And so there is a similar kind of schemes with classical verifier recently. This is again using this idea of learning with errors and using this trapdoor Claw-free functions. And so somehow you could use this trapdoor to put a leash on quantum computer, such that quantum computer doesn't know. As long as quantum computer cannot solve this problem and invert the functions, he will not be able to deviate from the actual strategy. And so with this, I just come to the conclusion that using this delegated quantum computation, the idea of my research, so basically this also like kind of an introduction. So what I'm trying to do is to work on 3 levels, and basically at the hybrid quantum networks, classical networks level, to see what kind of physical systems are suitable for what kind of models, and to use tools from classical and quantum cryptography of verification and compiling and so different levels of abstraction to give different levels of cryptographic applications that would be cloud computing or testing quantum devices and stuff like this. And yes, thank you so much for listening. And yeah, if you have any questions, I can take it now, or you can also email me or write to me, and I'll be happy to answer.
Anybody wants to ask anything? Yeah, thank you so much, Atul sir. It's a wonderful session. Hope our participants will be benefited. And as I mentioned that many of the participants joined late, please tell about yourself, about your research within 1 or 2 minutes, so that
Yeah.
they will know about it.
Yeah, so I'm a research fellow here at University of Maryland. and I was a postdoc before at Edinburgh and PhD in Singapore with Joe Fitzsimons. And so I have been working on this secure cloud quantum computing and like secure multi-party computation for the last 7-8 years. And now I'm slowly, so I used to work on information theoretic security in my PhD. And in my postdocs and the current work, I've been trying to use classical cryptography to see what kind of quantum cryptographic systems we could bring closer to reality. And this is the kind of work that I've been interested in mostly. And I've also worked on quantum information theory a bit, but that's just on the side. But yeah, mostly I work on like quantum cryptography beyond key distribution.
Thank you so much, Atul sir. It's a wonderful to have you, and obviously it is probably 1 o'clock early in the morning in US. So thank you so much. Around 75 participants, they have listened to you and hope they will be benefited. And probably if they have any doubt, then obviously they'll directly contact you.
Yes, definitely. Thanks.
So
Thanks a lot.
let us thank Atul sir for being with us. It's a wonderful session. Thank you so much, Atul ji. Namaskar. Okay.
Thank you.
Have a nice sleep. Okay.
Yes. Thank you so much. Bye.
Okay. Thanks a lot. Okay.